Thanks, Mia. Okay, next up, last talk of the day, Anaïs Barthoulot is going to talk about augmented broadcast encryption from identity-based encryption with wildcards.
Okay, so thank you for the introduction. I'm glad to see that some people are still here for this last talk of the day. My name is Anaïs Barthoulot, and today I'm going to present you the work entitled Augmented Broadcast Encryption from Identity-Based Encryption with Wildcard. This work was done with Olivier Blasi and Sébastien Canard. So I will start this talk with an introduction to present the primitives that we studied in our work and our contributions regarding those primitives. So the first primitive we will talk about is called broadcast encryption, or BE for short. A broadcast encryption scheme is an encryption scheme that allows to send a message to a whole specific subset of users, such that only users in that subset can recover the message. In the example presented here, we encrypt a message for a subset S, which is represented in blue. Thus, only users in blue can recover the message. Notice that in such a scheme, each user is identified by an index I that belongs to the set 1 to n, where n is the number of users in the scheme. Regarding security, a BE scheme must satisfy undistinguishability security. This property can be defined with a security game between an adversary and a challenger. The adversary gives to the challenger two messages A and B along with a subset S. Then, the challenger will pick one of the two messages and returns to the adversary the encryption of the chosen message for the given subset. The aim of the adversary is then to guess from the challenge ciphertext which message was encrypted. To help him, he can query some secret keys at the condition that they do not decrypt the challenge ciphertext in order to avoid trivial attacks. The second primitive we will talk about is called augmented broadcast encryption, or AUGBE for short. An augmented broadcast encryption scheme is a broadcast encryption scheme such that the encryption algorithm takes an additional input, which is an index int that belongs to the set 1 to n plus 1. Thus, now the message is encrypted only for users in S that have an index greater or equal to int. If in the previous example we represent in purple users having an index greater or equal to int, then we notice that only people that are both blue and purple can recover the message. Also notice that this is the original definition of AUGBE, in which there is only one encryption algorithm. In a more recent definition, there are two encryption algorithms, but we won't use this definition in our work. Regarding security, such primitive must satisfy two properties. The first one is called message hiding security. It is also an undistinguishability security game where the aim of the adversary is to guess from the challenge ciphertext which message was encrypted. Notice that this time the challenge ciphertext is created with the encryption algorithm and an index equals to n plus 1. So, as there is no indices that are greater or equal to n plus 1, that means that all keys won't be able to decrypt the challenge ciphertext. Thus, the adversary can query all the secret key he wants. The second security property an AUGBE scheme must satisfy is called index hiding security. In this security game, this time, the adversary has to guess which index between int and int plus 1 was used in the challenge encryption. To query he can this time query sequence keys that will fail, but either can success to decrypt the challenge ciphertext. The only condition to avoid trivial attacks is that if the key for secret index int is queried, then int must not belong to the subset S chosen by the adversary. So in our work, we introduced a new security definition that we called anonymous security. We can again see it with an undistinguishability security game, and this time the aim of the adversary is to guess from the challenge ciphertext which subset was used. To help him, he can query some secret keys that will either fail or success to decrypt the challenge ciphertext. The only condition is that if a key is queried for an index that is greater or equal to int, then the index must belong in both subset A and subset B. And actually, and this is our first contribution, we notice that this security definition is stronger than index hiding. We can see it with a security reduction, where the aim is to build an anonymous adversary that will win the security game by using an index hiding adversary. This is possible if, for a given subset S and an index int, we define subset A as being the subset of all users in S that have an index greater or equal to int, and subset B is defined as being the subset that has all users of S that have an index greater or equal to int plus 1. Doing so, the challenge and ciphertext received by the anonymous adversary will match the challenge ciphertext expected by the message by the index hiding adversary, and thus the former will be able to use the later guess to win the security game. So our second contribution regarding those primitives is a new BE scheme that you can see here. Our scheme has constant size ciphertext and is adaptively secure in the standard model. We can compare it to the scheme of JKW18, who also has the same security level, has also constant size ciphertext, and is using asymmetric pairings as our scheme. The main difference is that in our scheme, the public key size is shorter, while the secret key size is bigger. And finally, our third contribution is a new OGBE scheme, following the original definition of OGBE. And as you can see, unfortunately, our scheme is not efficient, as all parameter sizes are at least linear in the number of users in the scheme. However, notice that our scheme is the first one to propose adaptive security in the standard model. So how did we obtain those two new schemes? Well, we used two new generic constructions of BE and OGBE from a third primitive that is called identity-based encryption with wildcard, or WIB for short. Let's see on an example how this primitive works. We consider three users in our schemes, user A, B, and C. Each of them has some attributes. So we associate to each user a pattern, which is a vector, and we decide to create the pattern as follows. At the first position of the pattern, we'll put a 0 if the user does not have a car and a 1 if it does. At the second position, we'll put a 0 if the user does not have a bike and a 1 if it does. And at the last position of the pattern, we'll put a 0 if the user does not have a pet, and a wildcard symbol, which is represented by a star if the user has a pet, as it can be any pet. For example, it can be a dog or a snake. Now, suppose that we want to encrypt a message for users having a bike. Then we will associate to the ciphertext a pattern that will be equal to 1 at the second position. And as we do not pay attention to the value of the other attributes, we will put the wildcard symbol at the first and the third position of this pattern. Doing so, only users that have also a 1 at the second position of their pattern, meaning that they have a bike, can recover the message. Therefore, only user A and C, as expected, can recover the message from the ciphertext. So here is the formal definition of a WIB scheme, and it is important that we have a look at the decryption condition. Suppose that we create a key for a pattern P1 and a ciphertext for a pattern P2. Then the key will be able to decrypt the ciphertext only if P1 belongs to P2, meaning that for all positions where P2 is not equal to the wildcard symbol, then P1 and P2 must be equal. Regarding security, such a scheme must satisfy undistinguishability security, and this property can be seen as the analog of the security for the BE that I previously introduced you. So now, how can we build broadcast encryption from WIB? Well, first we noticed that any subset S can be represented with a pattern P that belongs to the set 0 star to the n, such that P will be equal to the wildcard symbol at all positions that belong to the set S, and will be equal to 0 at all other positions. Let's see it on an example. We take n equals to 7. So you can see that pattern P is equal to 0, except at the positions 5 and 6, where it is equal to the wildcard symbol. So this pattern here represents the subset 5, 6. We also notice that under a few conditions that are written on the screen, any user identity I can be represented with a pattern pi that belongs to the set 0, 1 to the n. And this pattern pi will be equal to 0 except at position I, where it will be equal to 1. Let's see it on an example. We still take n equals to 7, and we create the pattern for user 4. Then you can see that this pattern is equal to 0 except at position 4, where it is equal to 1. Creating such patterns, we obtain an equivalence between the statement I belongs to S and pi belongs to P. Again, let's see it on an example. We can easily notice that P4 does not belong to P, as at the fourth position, both patterns are different, and 4 does not belong to the set 5, 6. On the other hand, P6 belongs to P, and 6 belongs to the subset 5, 6. So here is our generic construction of BE from wipe. The idea is to use a wipe scheme that has ciphertext pattern space equals to the set 0 star to the n, and key pattern space equals to the set 0, 1 to the n. Then the setup algorithm of the BE will be the wipe setup algorithm. The BE key generation algorithm will be the wipe key generation algorithm for pattern PI defined as we saw. The BE encryption algorithm is the wipe encryption algorithm for pattern P defined as above. And finally, the decryption algorithm of the BE is the wipe decryption algorithm. Regarding security, we proved that if the wipe satisfies undistinguishability security, then so does the obtained BE. We can see it with a security reduction. The idea is that if the wipe undistinguishability adversary chooses a pattern P that corresponds to a subset S, as we did before, then the encryption he will receive from the challenger, which is an encryption for pattern P, will match to an encryption for subset S, which is expected by the BE undistinguishability adversary. And so the security reduction will work. So now how can we build OGBE from wipe? Well, we first need to have a look at the decryption condition of the OGBE, and especially at the last part of it, which is, I recall, I being greater or equal to int. Well, actually, I being greater or equal to int mean, because of the conditions on the screen, that I belongs to the set int to n. Thus, we can rewrite the OGBE decryption condition with only one set, which is the intersection of the set S and the set int to n. Let's see it on an example again with 7 users. The subset S is equal to the set 2, 5, 6, and int is equal to 4. When user I belongs to the set S means that it belongs to the blue circle, and user I has an index greater or equal to int means that it belongs to the purple circle. Thus, if user I satisfies both conditions, then it will belong both to the blue circle and to the purple circle, meaning that it will belong to the intersection, which is the green circle composed of users 5 and 6. So doing so, we can construct OGBE from wipe. We will use a wipe scheme that has the same ciphertext and key pattern spaces as we did for the BE. This time, the OGBE setup algorithm is the wipe setup algorithm along with the wipe key generation algorithm for pattern PI defined as above and I being equal to 1 to n. And the encryption and decryption algorithm of the BE are the encryption and decryption algorithms of the wipe as we did for the BE. Regarding security, we proved that if the wipe satisfies undistinguishability security, then the obtained OGBE satisfies message hiding security. We can see it with a security reduction. This time, it is important to notice that an encryption for index n+1 expected by the message hiding adversary actually corresponds to an encryption for a pattern which is equal to 0. Thus, if the undistinguishability adversary sends to the challenger a pattern P equals to 0, he will be able to use the message hiding adversary guess to win the security game. But what about the second security property required for OGBE? Well, to obtain such other property, we needed a new property on the wipe that we called pattern hiding security. This property, as we will see, protects the pattern used during encryption. In our work, we prove that this property, if the wipe satisfies this property, then the built OGBE is anonymous. And as we saw in the introduction that anonymous implies index hiding, we will obtain that the built OGBE satisfies index hiding security. So here is our definition of pattern hiding security. It is, again, an undistinguishability security game where the aim of the adversary is to guess from the challenger ciphertext which pattern was used. He can, to help him, query some secret keys that will either fail or success to decrypt the challenge ciphertext. The only condition is that when a key is queried for a pattern, the pattern must either belong stars to both pattern A and B, or either do not belong star to pattern A and B to avoid trivial attacks. So here is our security reduction to prove that pattern hiding implies anonymous. Well, the idea is that for given subset A, B, and index int, if we define pattern A as being a pattern that corresponds to the subset which contain all users of subset A that have an index greater or equal to int, and if we define pattern B as the pattern corresponding to the subset which contain all the users of subset B that have an index greater or equal to int, then the pattern hiding adversary will be able to use the guess of the anonymous adversary, anonymous OGBE adversary, to win the security game. So now that we know how to build OGBE and BE from wipe, we need new wipe schemes that satisfy the conditions we saw in order to obtain the BE and OGBE schemes we saw in the introduction. So first, let me talk about dual pairing vector spaces. So let's take a prime P, a fixed constant dimension n, and a bilinear asymmetric pairing group of order P. Then two random bases B and B star of ZPN will be said to be dual orthonormal if bi.bj star is equal to 0 whenever I is different from j, and bi.bi star is equal to psi for all I, where psi is an uniformly random element of Zp, and it will be the same for all I. So notice that when n is greater than 1, the elements in B and B stars are actually vectors. These bases can be generated with an algorithm that is called dual, that we will use in the rest of the talk. And for those who are not familiar with dual pairing vector spaces, you have a small example here on how it works with a dimension n equals to 3. So how did we obtain our first scheme? Well, we started from the paper of KLL 018, who proposed the selectively secure constant size ciphertext wipe scheme. We first adapted to our key and ciphertext pattern spaces. Then, in order to obtain adaptive security, we used the idea of KLL 020 to use symmetric composite order bilinear groups. And finally, we moved our scheme to the asymmetric prime order bilinear group setting, thanks to the use of dual pairing vector spaces that we saw, and the works of Lefko 12 and CLL plus 13. So before to introduce you our scheme for the bravest of you, you can see here the notation of 4 different subsets that we will use in the rest of the talk. So here is our scheme, but don't be afraid because I won't detail it. The only thing to notice is that the dimension used for dual pairing vector spaces here is 4. And in the ciphertext, you can see that we have 2 elements. The first one, which is no, it's not working. So the first one, which is m.eg1, g2, etc. This one is actually one element of gt, and it's only one element because in the exponent you have bi star.bi, which is the scalar product of the 2 vectors. Thus, it's only one element. It's not a vector anymore. And in the second element of the ciphertext, is actually 4 elements of G1, as we have in the exponent element of the basis B. Also notice that in this scheme, in the key generation, we will only use elements of the base B star, while in the encryption algorithm, we will only use elements of the base B. So this is our first scheme, which is adaptively secure under the symmetric external Diffie-Hellman assumption. So how did we obtain our second wipe scheme to obtain our OGBE scheme? Well, we used our first wipe scheme on which we added the property of pattern hiding. To be able to do so, we wanted to use the property of orthogonality of dual pairing vector spaces as it is done in the work of OT12. So now the idea is that in the secret key, we will still only use an element of the base B star, but we will add another element, which is presented here. And in this element, we will only use, in this term, we only use elements of the base B for positions where the pattern is equal to 1. In the ciphertext, we will again only use element of the base B, but we will add another term, which is presented here, and in which you can see, and in which we only take element of the base B that corresponds to positions where the pattern is equal to 0. Doing so, if the key pattern belongs stars to the ciphertext pattern, we will have that the element added in the key and the element added in the ciphertext will cancel with each other, thanks to the orthogonality of dual pairing vector spaces. So that gives us our second scheme, which is adaptively pattern hiding under the external decisional linear assumption in G1 and G2. So here is our scheme for the bravest of you. You can see on the key generation and the encryption algorithm the two terms I just spoke about. And it is important to have a look at the dimension of the dual pairing vector spaces, as this time it is equals to 4n plus 2. Unfortunately, doing this leads us to a new scheme that has all parameter sizes that are at least linear in the number of users. So now let me conclude this talk. In our work, we proposed two new generic constructions of broadcast encryption and augmented broadcast encryption from identity-based encryption with wildcard. We proposed a new constant size ciphertext wipe, which leads to a new constant size ciphertext broadcast encryption scheme. And by constant, I mean that the ciphertext is composed only of 4 elements of the group G1 and 1 element of the group GT. We also proposed the first wipe scheme that satisfies pattern hiding security, a new security property we introduced. That leads us to a new OGBE scheme, which unfortunately has parameter sizes too big, but is, however, the first scheme that is adaptively secure in the standard model. Regarding future works, well, we first would like to build more efficient pattern hiding wipe instantiations in order to obtain new OGBE schemes that are more efficient and that we hope will still be adaptively secure in the standard model. Finally, we also would like to build, for example, lattice-based wipe schemes that have either constant size ciphertext or satisfy pattern hiding security in order to obtain quantum-resistant broadcast encryption and augmented broadcast encryption scheme. Thanks for your attention. If you have any questions, please be my guest.
Great, thank you very much for your talk. Questions? Behind you. Behind you.
So, my apologies, maybe I didn't understand well the basics of how this scheme works, but what about the key exposure? Let's, well, think about the n users and n-1 users have exposed their keys. Is the security of the nth user, well, somehow affected by this?
You mean if the n users are colliding to break the scheme?
Well, n-1 have exposed the keys, but nth user have not. Is here security, well, security of his messages,
Well, as the message is the same for all users, if you are unauthorized users and your key is being exposed, well, everyone can decrypt the message if it is encrypted for you. But in order to prevent this, if I'm the authority and I know that you have been exposed, well, I will change, for example, in the OGBE scheme, I will change the index int use in order to exclude you from the scheme, and thus your key won't work anymore for the new messages.
I see, thank you.
Other questions? Do we have any online questions? No. Maybe you can help me with some kind of application scenarios where this broadcast encryption kind of techniques might be useful. I can think of satellite broadcast, for example, but maybe there are other application domains that
Yes,
right?
they are. So the idea was to build OGB scheme that is efficient. Unfortunately, we did not succeed to do it. But if some of you know, there is a generic construction of broadcast and frame scheme from OGB schemes. And our goal was to build at the beginning broadcast and traces schemes. As I'm working for a telecom company, thus we want to be able to broadcast paid television and be able to trace any traitor that will put a decoder on the internet for other people. That was the main application of our work, but unfortunately we did not succeed yet to have an efficient scheme.
Thank you. Any final questions? Wonderful, let's thank the speaker once more. So that's the end of the session for today. Do we have any final messages for everyone before we send them out? Tomorrow, 9 o'clock.
So tomorrow we start back at 9, but if anyone didn't register for the Desert Safari and is thinking to go, please, it would be better if we do it today so that we can organize it better. Thanks everyone for keeping it until the last minute. See you tomorrow.